And so sitting down here to finish off today, I'm going to try and convince you that logarithm functions, and I probably should leave the graph of the log function up rather than that one. Let me go there. This is the one we want to look at. These functions actually have some good uses, so I want to show you some uses of the logarithmic function now. So here we go. It says the magnitude of an earthquake is measured on a scale, and in fact it's a logarithmic scale called the Richter scale. I think we've all heard of Richter scale, have we not? And it says an earthquake of intensity I is said to have a magnitude m given by this particular equation here, log the base 10, and it's the ratio of intensity to some reference earthquake. And on this scale, in the 1908 San Francisco earthquake measured 8.25, whereas the 1989 earthquake measured 5.5. Was anyone here actually alive when that was on? Do you remember the earthquake? Yeah. I remember standing in my backyard. I shifted about that far when the earthquake happened. It was surreal. But anyway, bring back some memories, but that's just for me. Here we go. It says, compare the intensities of the two quakes. So let's make up some little notation here. So first of all, let IS be the intensity of the San Francisco quake. I must admit I'm not a seismologist, so I don't have a really clear understanding of the difference between magnitude and intensity. I don't quite know what they measure. Does anyone know? Anyone tell me? Got any seismologists? Sorry? No. I should look it up, but I didn't, so I'm just going to work with this equation because I know how to do that. I'm going to say let IN be the intensity of the Newcastle quake. So, we were told that the San Francisco quake measured 8.25. That's its magnitude. And so in terms of intensities, that's the ratio of IS to I0. Now what I want to do is I want to compare intensities. So I want to make IS the subject of this equation. And to do that I need to make IS the subject. To do that I need to use the inverse of the log function. And we know, in this case, I'm starting with the log function and going over here, so the inverse will be the exponential function. So to make things here, I therefore say 10 to the 8.25 will be IS on I0, and so that tells me that IS will be I0 times 10 to the 8.25. Do the same for the Newcastle quake. So I'll say and. The Newcastle quake had a magnitude of 5.5, that's what was reported. And so that says that the ratio of the intensity of the Newcastle quake to the reference quake, the log thereof, was 5.5. Again, log function, make IN the subject, use exponentiation to the base 10. And so I have 10 to the 5.5 is equal to IN on I0, which says that IN is I0 times 10 to the 5.5. And so now I can compare those. I'll take the ratio, if you like. So I'm going to take the ratio of the San Francisco intensity to the Newcastle intensity. So thus, the ratio of IS to IN is I0 10 to the 8.25 divided by I0 10 to the 5.5. The I0s will cancel out, with my indices here, I can, since I'm dividing two numbers with the same base, I subtract indices. And so this will become 10 to the 2.75. 10 squared's 100, 10 cubes 1,000, so this is going to be somewhere between 100 and 1,000. And when I got my calculator out, this one turned out to be about 562. So that says that the San Francisco quake was 562 times more intense than the Newcastle quake. So therefore, San Francisco quake approximately 562 times more intense. And as I say, I don't know what that means. I don't know how they actually measure what the intensity of a quake actually means. I should look it up.
Intensity is the severity of the shaking, and magnitude is the size of the earthquake at
The severity of the quaking, yeah. I don't quite know what they'd have a definite thing that they're actually measuring there. So that would be the informal version of it. But that's good. Well done. If you find something else useful in there, tell me. More intense, I'll say then Newcastle. I wonder if it's something to do with how much things shake or something. Or whether it's... Yeah. But anyway. Okay, so there's one use of things. Here's another use sitting here. So it says, here's some data about the planets. And it says in this data we've got the average distance of the planet from the sun, because the orbits are actually elliptical, they're not circular. So the distance does vary a bit, but they're very close to circular. The orbits, the eccentricity of the ellipses is quite small until you get out to Pluto and so forth. But anyway, so the average distance is about that in millions of kilometres, and then the time taken in days for each planet to travel around the sun once. So this is the number of Earth days, if you like, of each year of each of the planets. So if you live on Pluto, it takes 90,670 days in a year. So you don't get old, don't have many birthdays on Pluto, I don't think. But anyway, we're not on Pluto, so that's fine. It says, determine a suitable power law relationship between R and D. So a power law relationship is the key word in there. So a power law relationship is a relationship of the form. Now, what am I going? I'm going between R and D. I think what we wanted was I wanted D as some function of this form. So A and K are constants. So D is related to R by some power law. I want to find A and K. I want to find the K and I want to find the A. And if they're related like that, that's a power law. Now, that K doesn't have to be a whole number. We were used to, when we had polynomials, we said that, look, this, if K was a counting number, like D squared or R squared, R cubed, or whatever. But in this case, it can be any power whatsoever in here. So I'm trying to say, is there a relationship between these numbers here? And if you were to stare at them, there's certainly nothing obvious, just looking at them blindly. So let's do some mathematics. Now in here, given that I have an exponential type relationship here, I'm going to take the log of both sides. So if I do this, I can say then here log of D is equal to the log of A times R to the K. Now I can rearrange, this just represents a number, but I can rearrange this to represent the same number in a different way. Okay? So what I'm going to do here is I'm going to use my log laws. Log of x times y is the log of x plus the log of y. So this becomes the log of a plus the log of r to the k. So that number and that number are the same number, just written differently. This one I can also simplify using my log laws, or rearrange rather than simplify. So I can write this as log A plus K log R. So I might actually put this log D over here because I want to highlight that. So, if there's a power law relationship between D and R, when I take the log of D and the log of R, if I were to plot them, it should be a straight line with a y-intercept of log A and a slope of K. Is the conclusion from there. So thus, a plot of log D versus log R should be a straight line with slope K and y-intercept of log A. Think of this as y as being mx plus b, if you like. If I take the log of both sides and plot those points, and it turns out it's not a straight line, that tells me that there's no power law that's suitable. You have to look for some other, like it could be I don't know, all sorts of different things. It could be a polynomial, no, not a polynomial. Yeah, it actually could be a polynomial because we could have some extra terms on there. It could be a trig function, it could be all sorts of different things. Okay? But if there's something of this form that works, then this is what happens. So I go back up to here and I add in another couple of things. So I'm going to calculate the log of R and I'm also going to calculate the log of D. And for example, the log of 57.9, and I think I'll use log to the base 10. But I could use log base E if I wanted to. But here, this would be 1.7, I got here, 627. This one would be 1.9445. And do that all the way down. Down here you get 3.77, what do I get? 14. And 4.9575, and so forth. So I calculate two new columns and I plot these points. Here's my x coordinate, here's my y, here's my x coordinate, here's my y coordinate, and so forth. So I plot all those points and I'm hoping to get a straight line. And here's where I did it. And certainly on the scale that looks there, that line looks pretty darn straight. And so what I did was I then said, okay, what's the y-intercept and what's the equation, what's the slope of the line? You can work out the slope from 2 points. Given that you know a point on the line, you can work out the y-intercept. And so this line turned out to be 1.5x minus 0.7 in there. And in fact, even if these lines, I mean this one, certainly I made the dots big enough that it looks like it's perfectly on a straight line. But even if it's not perfectly on a straight line, because there's probably errors in things like this value here or this value here. So what we would do, we would say, if this is close to a straight line, not perhaps perfectly on a straight line, then we would just use the line of best fit here and say, look, I can model this stuff by a power law. That's a good fit. So in here, this is just the line of best fit of the points. Line of best fit. And sitting in here, my k, therefore, is going to be 1.5. That's the slope of that line. And log a is the y-intercept, and that is minus 0.7. So a is going to be 10 to the minus 0.7. And so that says if I use a power law of the form d is 10 to the minus 0.07 r to the 1.5, that should give me a good representation of these points here. And here's a graph of the original data and the model. And as you can see, so this is the graph of 10 to the minus 0.07 r to the 1.5. There's my original data points, and the graph fits pretty well to the original data. So you can see here the graph of the power law relationship, fits the original data well. And in fact, this 1.5, 3 on 2, it turns out that when Kepler, you heard of Johann Kepler? When he was doing his astronomy, he actually worked out that power law relationship back in the, I can't remember when it was, he's in the 1700s, 1600s. Anyway, a while ago, he worked out that this was a relationship that had a power of 3/2, he called it, and he made that into one of his laws of planetary motion, in fact. So this is actually a representation of one of Kepler's third laws. And then Newton came along and proved that Kepler's laws work if you make an assumption of gravity working via an inverse square law. So even though it looked like I made up the data so that I'd get a good fit, this is actually what happened. This is actually real live data and actually does work. And I think, is that all I've got? Or have I got one more? One more, okay. This is a very, very common use of logarithms because I've said here power law relationships, but you can test a whole pack of other different relationships by doing other log graphs, in fact. So if you're a person that gathers a lot of data in scientific settings, you'll be using this sort of stuff with logarithms all over the place. Because you'll plot the original data, you'll plot the log versus the log, then you'll plot the data versus the log and so forth. And depending on which one gives the best line as to what model you'll actually use. Okay, so experimental scientists use this all the time. Okay. And remember last time I said there was an accident in Chernobyl, and we found that the concentration, found a formula for that concentration, and last Tuesday I said to you, what happens when T is equal to 32? And I had to choose 32 at that stage because this bottom number there is an 8, and that made all my indices work nicely. Now that I have logarithms, I don't have to worry about fudging the numbers. And it says, so now I can answer this question, find how long it took for the concentration to fall to the safe level, which we called CS. So what I wanted to find here, so I want to find T such that the concentration C is equal to the safe level CS. I now want to solve that equation, and because I have logarithms, I can now solve that equation quite happily. So that says, sitting in here, when I want to find T such that CT is equal to CS, so I want to solve CS is equal to 10 times the safe level, because that's what it was at the beginning, 2 times minus t to the 8. I want to solve that for t. So solve for t. This is an exponential function, and I know that to solve an exponential function I will use the inverse, and the inverse of exponential is log. So I'm going to use a logarithmic function here. But before I do, it would make some sense to actually divide both sides by cs. And in fact, I'll divide both sides by 10 cs. And so here I'll get 1 on 10 is equal to 2 to the minus t on 8. And now I'm going to take logarithms. You can use logarithms of whatever base you like, but I suspect in here I'm going to need an approximation at some stage, so I'm going to use log to the base 10. But you can use log to the base e, log to the base 2, whatever log you like. So I'm going to take log of both sides, take log of both sides, and so I'm going to use log to the base 10 is log to the base 10 of 2 to the minus t on 8. Now in this case it just so happens that that 10, and that's a 10 there, usually that number would be something awkward and you just work that out with your calculator. But here I can actually do this exactly. What power must 10 be raised to give 10 to the minus 1? The answer is minus 1. So I can actually write that sitting there. So I've got minus 1. On this side, I'm going to use my log law that I've had before. N log x is equal to log x to the n. So this becomes minus t on 8 log of 2 to the base 10. That's supposed to be a t sitting there. So I'm going to divide both sides by log 2, multiply both sides by minus 8 in here. So I can say t on 8 multiplied by the minus 1 is 1 on log 2, and so t is equal to 8 on log 2. And if I work that out on my calculator, hopefully I get something like 26.58 to 2 decimal places. And so I figure it takes around 27 days for the concentration to drop to the safe level. So it takes around 27 days for the concentration to drop to a safe level. And as I say, we could do that via our log functions.